Let's first of all talk about the history of the periodic table. There was a 4th century Greek philosopher named Democritus, who's kind of the first one that suggested the term atom. The word atom in Greek means unable to be divided. So this Democritus didn't have any technology to prove his idea. He just thought that there was such a thing as a smallest portion of everything that just could not be divided. And in idea, he was kind of right on track. He did think that the atom could not be divided, but that would be proven wrong. So he at least was getting there. Fast forward 1,400 years or more to the 1800s. In 1808, an English school teacher named John Dalton proposed that there were atoms that could not be divided, and the atoms of the same particles were exactly alike. So if you had oxygen atoms, every oxygen atom would be the same. So that's going a little bit farther than Democritus did. Plus, John Dalton also had the concept of molecules, that these little bitty particles, these atoms, could form together and make some kind of compound, and that you have what's called a molecule of that compound. And that's something that Democritus had not proposed, and Dalton was on the right track as well. But Dalton also thought that the atom could not be split up. And one thing we have found out since is that the atom can be split up. We have the nucleus of the atom, which has these positively charged protons. In blue you can see these neutrons, which don't carry a charge. And then around outside the nucleus are these negatively charged electrons. So that's something we've come to know since. And Niels Bohr, who was alive in the early 1900s, he was around whenever it was understood about protons, electrons, and neutrons. So Niels Bohr came up with the idea of electron energy levels. These energy levels, well, it takes energy, according to Niels Bohr, for electrons to move to the outermost level. Well, here's what I'm talking about. Here you have the nucleus, which is, well, it has the protons and the neutrons. And the electrons out here, you have more than one level. You have more than one level where the electron could be. The electron could be on this level, the electrons could be on this level. And he said that for them to be on their outermost levels, you have to have some kind of energy that goes with it. So these electrons, the faster they are moving, the farther out they are. And he was getting there. It's not completely true, but he was right that they do appear to have energy levels. And that's something that will be shown even more on the periodic table, that there are different levels, and the different elements will determine what level these things are at. So Niels Bohr came up with that the energy levels are closer together. Oh, I'm sorry. The higher up you get, the farther out you get, the closer the energy levels are. And I think one of your textbooks is going to have it like a stairless building, that the closer you get to the top, the smaller the floors would be. That's not always true with buildings, but that's kind of how Niels Bohr saw it. But anyway, it takes energy for electrons to move to the outside level. The higher energy levels are closer together. We now believe that these electrons that are showing up in both of these diagrams are more like waves. And the term electron cloud kind of comes to mind, and you hear that a lot. Scientists now think that electrons are like fan blades. Here we have a fan, and I don't know if you can see very well or not, but this fan is going, and you can kind of see the faint part of the fan blades right here. The blades are going so fast that you can't really see the individual blades, and scientists think that that's how electrons are, that they are going so fast that if you could see on the subatomic level, that you could not see them, that they are like a blur, like a cloud, and hence the term the electron cloud. Orbitals have to do with these electrons. Now, orbitals doesn't have anything to do with how fast they are. They have to do with where they are. Now, orbitals is a little bit complicated. So let me try to go slow. There is what's called an s orbital, where electrons reside, 2 of them, by the way. There are p orbitals, where electrons reside. There can be 2 in this level, there can be 2 in this level. They look kind of like a dumbbell in the p orbitals. And there are also d and f orbitals, which are a little more complex in looks and a little more complex in understanding. So we're going to try to hit the s and the p orbitals. Down below here is a periodic table. A periodic table, I'm sure you've seen them before, and wow, we will study them a lot in this class. A periodic table has a lot of organization to it, and part of the organizations have to do with these orbitals. If you have, say, a hydrogen atom, the hydrogen atom has in its nucleus 1 proton and 1 neutron. I believe I'm right that it has 1 neutron. I know it has the 1 proton right here. But anyway, it has the 1 proton on the inside, and outside it, it has the electron. In its energy level, it's only going to be in the s level. The s level is the lowest level. Hydrogen only has that s level because it just has 1 electron. If it had more electrons, it might be in another level. For example, this lithium. Lithium here has 3 protons, 3 neutrons in the nucleus, 3 protons, 3 neutrons, and it will have 3 electrons. Now, 3 electrons are too many to fit in the s orbital. So 2 of those electrons are in an s orbital, and the outer one is in the p orbital. So kind of using Niels Bohr idea, kind of slowing these electrons down, you have all these electrons that are filled up in the s orbital. The s orbital cannot hold more than 2. Pardon me.
Could you come to Miss Brown's office, please, Miss Fowler?
Now you can tell I'm at school making this video. But anyway, you have these 2 electrons right here. They have filled up this s orbital. So you have 1 that is in the p orbital. And that kind of electron is going to be called its valence electron, and we'll talk a little bit more about valence electrons in a little bit. But you probably have figured out every single element in this column is going to have 1 in its outer orbital, in its outer electron shell. Now, fortunately, you'll find that these also are that way as well. You know, I think I just told you something wrong. I'm sorry, we have the 2 s orbitals. So lithium here has 2 in this s orbital and 1 in this s orbital. Sorry, the only thing I told you wrong was the difference was saying this was a p orbital. This is also an s orbital. But take a look over here. You have boron. Boron should have 5 protons in the nucleus, and it will have filled up the 2 in its s orbital. It will have filled up the 2 electrons in its other s orbital, and that's where you will get to the electron in the p orbital. So it has that valence. The outer is going to end up being 3 because you're going to add these last 2 together, because we'll get to that in the valence. But anyway, we have hydrogen, lithium that have just in the s orbital, and B actually gets into the p orbital. Now, D is going to have to do with these elements down in here, and we're not going to touch these elements much right now. And F is going to have to do with these elements here, and we're not going to touch them much right now. So you need to know that there are orbitals, the S, the P, the D, and the F, and the outer electrons are going to fill up, or all the electrons are going to fill up those orbitals. And it's easier, I mean, to me, knowing that P is in the shape of a dumbbell doesn't tell me as much as how many electrons are in there. Because what's going to happen is when you start putting these elements with each other and making these compounds, that's where those electrons are going to come in handy, you knowing, not necessarily what shape it's going to be in. So know that you have s orbitals and p orbitals that we will be dealing mostly with, and that those electrons are in those energy levels, those particular orbitals, the p and the s. Mentioned valence electrons. If you were to look at the periodic table, each group has a certain number of valence electrons. This has 1, this has 2, and so on. And I'm going to go back to Niels Bohr model. The valence electrons are what's going to be in the outermost shell, and they're the ones that will interact with other elements. All of these down through here, their shell is filled. You'll find in the next video that these are not going to interact much at all. But in this case, this column has 7 as its valence electron. They need just one more to fill up their shell, and you know which one they're going to interact with. This whole column has just one left, just one extra. So you'll find that elements from this column end up partnering and making compounds with elements from this column. That's part of what you like about the periodic table, is you just have to look at places to see which ones are going to combine. This column here will combine a lot with this column here, and so on. Now, you will probably come across the term Lewis dot, let's see, what's it called? Lewis dot diagrams, I believe it's what it's called. But this may be a way to help you remember some of these. And what it does, it takes what we already know and makes a diagram, and the dot here is going to represent the outermost shell. So here, every one of these in this first column in the periodic table has just one dot outside their symbol. So they all want to get rid of that one. And I think we mentioned this table here. They have all except one. They have 7 on the outer side. Now, one thing you may notice is we did not include anything in these D and F orbitals. Let me go back to where we had a periodic table. Yeah, we did not include anything from these D and F orbitals here. So all that area there is just something we're going to deal with in time. And they just don't match up very well with the other elements. You're not going to find as many compounds with them. But whenever we look at this Lewis dot structure, it's talking about column 1, column 2, then 3, 4, 5, 6, 7, 8, like right over here. And those are the ones we're going to be looking at most. And what you can see now from these Lewis dot diagrams is the outer shell. This shows you what's in the outer shell of all of these. And hey, notice what's happening here. All of these are completely full. So they don't want to have the interaction with these others. And hopefully that gives you a little bit of a basis for what the periodic table shows, where the elements are, where the electrons can be found in each of these where the electrons can be found in each of these elements, and a little bit about how they're going to match up. Well, I hope you learned a little bit about the periodic table. We will be saying more about it.